In the quiet language of physics, the universe is described not as a story, but as a set of numbers. Not the numbers we invent to count objects, but numbers that seem to be built into reality itself. They do not live in any one place. They do not appear written on the sky. And yet they govern everything: how strongly matter attracts matter, how tightly electrons cling to atoms, how quickly the early universe expanded, how stable the nuclei inside stars can be. According to modern physics, the cosmos is not merely large and old. It is also delicately arranged. Its fundamental behavior depends on a small collection of physical constants and laws that appear to sit inside extremely narrow limits. Shift them slightly, even by tiny fractions, and the universe that follows is no longer one that can make complex structure. It might expand too quickly for galaxies to form, collapse too soon into a featureless density, or remain a thin haze of particles that never condense into stars and planets. In this sense, the universe resembles a system balanced on a knife edge, where the existence of long-lived structure seems to depend on precise conditions. This observation does not begin with life. It begins with something even more basic: the fact that there is a stable something rather than a uniform emptiness. Galaxies exist. Stars shine for billions of years. Chemistry forms patterns more intricate than simple gases. Planets can cool, retain atmospheres, and host long chains of reactions. All of that rests on the interplay of forces that, in our universe, happen to cooperate. There are four fundamental interactions commonly discussed: gravity, electromagnetism, and the strong and weak nuclear forces. Each has a distinct role. Gravity is the architect of large-scale structure, pulling diffuse matter into clumps, building galaxies, shaping stars, and guiding planetary orbits. Electromagnetism governs atoms, chemistry, light, and the interactions of charged particles. The strong nuclear force binds protons and neutrons into atomic nuclei, allowing the diversity of elements to exist. The weak nuclear force enables certain kinds of radioactive decay and plays a critical role in nuclear processes inside stars. We usually take these forces as given, as if the universe could not be otherwise. But physics allows us to imagine alternatives. It is possible to describe a universe in which the same basic framework exists, but the constants that set the strengths of these forces are slightly different. And when physicists run that thought experiment, the results can be startling. Small changes in physical constants would result in profound differences, not just in the details of nature, but in whether nature can build complexity at all. Consider gravity. In everyday life, it feels strong because it holds us to the ground and keeps oceans in their basins. But compared to other forces, gravity is extraordinarily weak. On the scale of particles, electromagnetism dominates. That disparity is not a trivial curiosity. It matters for how stars behave. Stars are a negotiation between gravity and pressure. Gravity pulls inward, trying to compress a star's mass into a tighter and hotter core. Pressure, produced by heated matter and radiation, pushes outward. When the balance is right, a star can settle into a long-lived stable state, burning nuclear fuel slowly enough to shine for billions of years. If gravity were stronger by a modest factor, stars could become smaller, hotter, and burn their fuel much faster. The universe might fill with short-lived stars that flare and die before planets have time to cool and stabilize. If gravity were weaker, matter might struggle to collapse into stars at all, leaving the cosmos dim and diffuse. Then there is electromagnetism, the force responsible for chemistry. Its strength shapes the size of atoms, the energy levels of electrons, and the behavior of molecules. Chemistry depends on a delicate middle ground. If electromagnetic interactions were significantly stronger, atoms could hold electrons too tightly, making complex chemistry less flexible or harder to form. If it were weaker, atoms might not hold together reliably. The bonds that make molecules stable could fail, leaving no robust chemistry to build complexity from. The strong nuclear force introduces another layer of precision. Inside atomic nuclei, protons repel each other electrically, since they carry the same charge. If electromagnetism were the only interaction at work, nuclei would fly apart. The strong force counteracts that repulsion at extremely short distances, binding protons and neutrons together, but its strength cannot be arbitrary. If the strong force were slightly weaker, some nuclei might be unstable, limiting the range of elements that can exist. If it were slightly stronger, nuclear reactions could proceed too easily, changing how elements form in the early universe and inside stars. In some imagined universes, hydrogen might not remain stable in the way it does here, or the steps that allow stars to fuse hydrogen into helium might not operate in a gentle, sustained way. Even the simplest element, hydrogen, turns out to be a kind of cornerstone. In our universe, hydrogen is abundant and stable, and it fuels stellar lifetimes. It is also a key ingredient in water and organic chemistry. If the relationships among particle masses and force strengths were different, hydrogen might be less common, less stable, or behave in unfamiliar ways. The entire chemical landscape could shift, not by degrees but by categories. The weak nuclear force, less intuitive in daily experience, also matters. It controls certain decay processes and is part of the chain of reactions that power stars. The early universe, too, depended on weak interactions to set the balance of protons and neutrons shortly after the Big Bang. That balance influenced the primordial production of elements like helium. If the weak force were different, the early chemical inventory of the universe could change, affecting the raw materials available for later structure. And above all of these sits a deeper parameter that shapes the universe at the largest scale, the rate at which space expands and the energy that seems to be associated with empty space itself. In modern cosmology, the accelerated expansion of the universe suggests the presence of something like dark energy, often modeled through a cosmological constant. This is one of the most striking examples of apparent fine adjustment. According to simple theoretical expectations, the vacuum energy of space might be enormous. Yet observations indicate it is very small, but not zero. Small changes in this value would result in a universe that either expands so rapidly that matter never condenses into galaxies, or collapses so quickly that it ends before complex structures can develop. When physicists talk about this, they are not describing a minor inconvenience. They are describing a world where the basic storyline of cosmic evolution never begins. No galaxies, no stars, no stable planetary systems. No long-lived environments where complexity can accumulate. It becomes harder to see these constants as mere background settings, and easier to see them as boundary conditions on what kind of universe can exist. This is where the fine-tuning hypothesis enters the conversation. In physics and cosmology, fine-tuning is not a claim about intention, it is a description of sensitivity. A system is fine-tuned if its behavior depends strongly on parameters taking values in a narrow range. If most possible parameter values lead to a simple, lifeless, or structureless universe, while only a tiny range yields a universe rich with complexity, then the existence of that complexity becomes a fact that calls for explanation. Some scientists suggest that fine-tuning is a real problem because it sits uneasily with the expectation that fundamental constants should not need to be delicately chosen. In many areas of physics, when a theory requires parameters to be adjusted with extraordinary precision, it signals that something deeper may be missing. It might mean there is an underlying mechanism that forces the parameters into the required range. Or it might mean our assumptions about what values are possible are incomplete. In this sense, fine-tuning is less a conclusion than a question. Why are the constants what they are? Are they fixed by necessity, determined by deeper laws that could not be otherwise? Or are they contingent, the result of some cosmic lottery in which many universes exist, each with different settings, and we find ourselves in one of the rare places where complexity is possible? One possible explanation is the multiverse. In some versions of modern theoretical physics, particularly those connected to inflationary cosmology and certain interpretations of high-energy theory, it is possible that our universe is not the only one. Instead, the larger reality might contain many regions of spacetime, each effectively a separate universe with its own values of physical constants, its own low-energy physics, perhaps even different numbers of dimensions or different particles. If the multiverse exists, then fine-tuning could be explained statistically. We should not be surprised to observe a universe compatible with observers, because only in such a universe could observation occur. This line of reasoning is sometimes called an anthropic explanation. It does not claim that the universe was designed for life. It claims that our observations are conditioned by the fact that we exist to make them. If there are many universes, the argument goes, then it is possible that we inhabit a rare one where the constants allow complexity, simply because such universes are the only places where questioning beings can arise. In principle, this offers a rational response to fine-tuning. It reframes the problem. Instead of asking why this universe has such special parameters, it says, in a vast ensemble of universes, some will have these parameters, and we will inevitably find ourselves in one of them. But the multiverse remains controversial, and for reasons that go beyond personal taste. The most serious concern is testability. Science is grounded in the ability to compare predictions with observations. A proposal that cannot, even in principle, be connected to evidence risks becoming a philosophical interpretation rather than a scientific theory. Some multiverse models may have indirect consequences, but others place alternative universes beyond any observational horizon, permanently inaccessible. In that case, the multiverse is not easily falsifiable. It becomes difficult to distinguish it from a story constructed to explain an uncomfortable coincidence. There is also a technical challenge. Even if a multiverse exists, making statistical predictions requires knowing how to count universes and assign probabilities. In an infinite multiverse, this measure problem becomes subtle. Different ways of counting can lead to different conclusions. The explanation risks becoming flexible in the wrong way, capable of fitting what we see without uniquely predicting it. And yet, some physicists take the multiverse seriously because it emerges naturally from equations that are motivated by other successes. If inflation occurred in the early universe, it may lead to a process where different regions undergo different outcomes. If high-energy physics allows many possible vacuum states, it may imply a landscape of possibilities. In that picture, our universe could be one realized option among many. The idea is intellectually coherent, and in some frameworks it may even be the most straightforward interpretation. But it remains, at least for now, a frontier concept. It sits at the boundary of physics and philosophy, where the usual tools of experiment and observation become difficult to apply. This is part of why the fine-tuning discussion is uncomfortable. Fine-tuning challenges a traditional scientific instinct, the hope that the universe is not only lawful, but also natural in a deeper sense, not requiring improbable coincidences. When parameters appear delicately set, we are faced with choices, and none are entirely satisfying. One choice is to accept the coincidence, the constants are what they are, and there is no deeper reason. Another is to propose an underlying structure that makes these values inevitable. Another is to expand the reality we consider, introducing a multiverse where our universe is not special in the full ensemble. Each option carries a cost. Accepting coincidence can feel intellectually incomplete. Physics has a history of replacing coincidences with mechanisms. When planetary motion seemed complicated, deeper laws simplified it. When electricity and magnetism seemed separate, deeper theory unified them. When the stability of atoms was mysterious, quantum mechanics provided structure. In that tradition, unexplained fine-tuning resembles a signpost pointing toward missing physics. But proposing a multiverse trades one kind of unease for another. It may provide a statistical explanation for why we observe certain conditions, but it can also remove the possibility of direct confirmation. It asks us to loosen the usual standards of empirical access, at least temporarily, and to consider explanations that may never be tested in the conventional way. Meanwhile, searching for deeper underlying laws is an active scientific project, but it remains uncertain whether it can succeed. It is possible that the constants we call fundamental are not truly fundamental. They may be the result of deeper dynamics, frozen into place as the universe cooled from its earliest, highest energy state. If so, then what looks like arbitrary tuning might be a consequence of a process we do not yet understand. It is possible that certain relationships among constants are constrained by mathematical consistency. In some theories, not every combination of force strengths and particle masses is stable or coherent. Some combinations might lead to inconsistencies, runaway behaviors, or universes that cannot exist in a stable form. If the space of possible universes is already limited by deep constraints, then our universe might not be as improbable as it seems. The apparent fine-tuning could partly reflect that the underlying framework only permits a narrow class of outcomes. There is also the possibility that we are misreading what counts as fine-tuned because we measure everything against the existence of life as we know it. Our forms of complexity depend on long-lived stars, rich chemistry, and stable environments, but we do not know the full range of complexity that might be possible under different conditions. Even so, the argument is not solely about life. It is also about structure, the formation of atoms, the assembly of galaxies, and the existence of stable, differentiated matter. Those features appear tied to specific balances among forces. When physicists model alternative universes, they are not merely imagining minor changes. They are exploring the stability of physical reality. In many cases, the result is not a different kind of life, but a universe where complexity cannot take hold in any familiar sense. A universe might be filled only with light and expansion, or it might collapse into dense black holes, or it might form only simple particles with no stable atoms. The cosmic environment could be too chaotic, too short-lived, or too uniform for layered structure to emerge. So the question returns, quietly, without rhetoric, why these numbers? Why gravity so weak compared to electromagnetism, allowing stars to burn slowly? Why strong force that binds nuclei, but does not lock all matter into a single heavy element? Why an expansion history that permits galaxies to form? Why a vacuum energy small enough to allow structure, yet not exactly zero? In the fine-tuning discussion, it is essential to remain cautious. The universe is vast, and our understanding is partial. Some claims about sensitivity may depend on assumptions about how constants vary together. Changing one constant while holding all others fixed may not correspond to a physically meaningful alternative. In deeper theories, parameters could be linked. A change in one might entail changes in others, potentially preserving some forms of structure. What looks like delicate tuning in a simplified analysis might look different in a complete theory. And yet, even with caution, the pattern persists across many lines of inquiry. The existence of complex, long-lived structure appears to depend on a set of conditions that could plausibly have been otherwise and that occupy a narrow region of possibility. This is where the conversation shifts from calculation to interpretation. Structure or coincidence? Are we seeing evidence of deeper order, a sign that the constants are not free to vary independently, but constrained by a more fundamental layer of law? Or are we seeing the outcome of chance, made meaningful only because we are here to notice it? Some scientists suggest that the discomfort we feel is a clue. It is the same discomfort that has guided physics before, the sense that a coincidence is asking to be explained. If fine-tuning is real, it may point toward new principles, perhaps a deeper theory that fixes the values of constants the way geometry fixes certain relationships in space. In that view, what seems precarious might be inevitable, not because of purpose, but because of necessity. Others argue that the multiverse, however unsettling, may be the simplest extension of current theories. If cosmic inflation and high-energy physics naturally produce a variety of universes, then statistical selection becomes a reasonable framework. We may not like the idea, but nature is not obligated to fit our preferences for clean, testable stories, and still others emphasize humility. They note that physics has not yet fully united quantum theory and gravity, and that many of the deepest questions remain open. The constants might not be constant in the way we assume, or our current models may be approximations that break down at fundamental scales. Fine-tuning might be a symptom of our incomplete understanding rather than a feature of reality itself. What remains at the end of all this is not an answer but a boundary. Fine-tuning sits at the edge of what modern science can currently explain with confidence. It touches cosmology, particle physics, quantum theory, and the philosophy of scientific explanation. It forces us to confront what counts as an explanation in a universe where we have only one observable example.